My name is Joshua Griffith. I'm presenting on behalf of the Silver team for our spray paint booth pressure system. Background, the paint booth is in Dunlap, Tennessee at a facility that spray paints their engine housings. Our booth is set up to where both the dampers are closed, so we're only fooling with booth one. The input is the M input is the motor power, that is our one variable. The output is in centimeters per H2O for the pressure. This is the procedure for when you have the operating system. The operator input goes into the controller program. It's run to it and output it to an Excel spreadsheet. Overview of it, I'm going to review the information that we came up with over the course of the semester, and the new stuff that I'm going to be presenting on is for the proportional only control of the modeling, the experimental data, and the proportional integral controller model. This is the steady state portion of the operating curve for ours. It showed how we came up with our steady state operating curve. Also show how we collected the data for our step response. Use that to go into the FOPDT modeling for the step response. That got it to where we can run into our frequency response modeling. And this, where we could find the dead time constant, led us to our Bode plots. This helped us set up to where we got into our new system parameters, and with our the Bode modeling. This shows that the different K values, tau values for the time constant and dead time from the system. Came down to these system parameters, which we've used throughout the last few, the proportional only modeling and the root locus modeling. Root locus help us determine our K values for our critical dampening, the 1/500th decay, 1/10th decay, quarter decay, and the ultimate. These parameters were then put into our proportional only control modeling. These were used to find the decay ratios, settling time, and offsets. Also determine whether the system was operating monotonic or oscillatory. Your decay ratio is the ratio between the height of the spike from your second curve to the second, divided by the height of the first one. Your settling time is the time it takes for the system to go from the spike or the step in the input down to where it goes back into steady state. The offset is the distance between the output and your set point. And on this one, it's oscillatory. This gave us our decay ratio, settling time for our lower, middle, and upper ranges. We use those numbers, go in and try to reproduce the models in with the physical system. Our system, due to where we don't have a whole lot of data points, it came out to where you can't really tell when your system is actually that much stable, because you can't get decay ratio and settling time. It doesn't look like it's settled. You can't get decay times or the decay ratios very well off of that. The right side is the model data. The left side of the table is the experimental data that we have. Looking at the offsets, the lower range, it jumped from where it was offset below to above, but it never wanted to get to the actual set points. The same with the middle and the upper ranges always stayed below until you got to the higher K values. And the decay ratio is just, especially on the upper range, it didn't want to settle at all. Everything was spiking due to the uncertainties in the system. From that, we went into the proportional interval control modeling. This was set up to where you use the same system parameters as you did on the first root locus, but you're using these to create a new root locus in association with the new tau value. The tau value for that can be found one of two ways. Either you take your initial tau value from your system parameters and divide that by 1.2, or you take your initial dead time and times that by 3.333. And this came up with new K values for your critical dampening, 1/500th, 1/10th, and quarter decay, and your ultimate. Comparing those to the first root locus, for most of our ranges, it would see that you would have your K values for the tau were greater than what the K values were from a root locus, but that's not true for the lower range. Lower range, your new Ks were somewhat lower than what they were from the first root locus. Conclusion, we use the K values to use the K values from the root locus to do the proportional only controller, ran the experiments, try to reproduce what we got from the model in the physical system. Some of the values were inconclusive due to the uncertainties in the system itself. Used the same system parameters to develop the new root locus for the proportional interval controller and compared the new root locus to the first one.